Hello friends, I am Professor Swamin Dongre, and in this video we'll see the application of BJT as a switch. As we know that in BJT there are two PN junctions. One is emitter base junction and second is collector base junction. If both junctions are forward bias, BJT operates in saturation region, and in saturation region it acts as a on switch, close switch. If we reverse bias both the junctions, then BJT operate in cutoff region, and in cutoff region it acts as an open switch, off switch. So depending on the biasing, we can use the BJT as either on switch or off switch. Here we will consider the most widely used configuration of BJT, that is common emitter configuration, because it is having moderate voltage gain, moderate current gain, and hence its power gain is more as compared to the common base configuration and common collector configuration. And in common emitter configuration, we will consider the NPN transistor, because in NPN transistor, majority charge carriers are electrons, and electron mobility is greater than the hole mobility. So that is why we will consider the NPN transistor. In common emitter configuration, we have seen the circuit diagram. There, emitter is common, base is the input terminal, then the collector is the output terminal, and with the help of two DC supplies, one at input side, second at output side, we have done the proper biasing of that common emitter configuration. Now here I will draw some modified circuit, a simple circuit, so that you will come to know how this BJT can be used as a switch. So see the circuit first. So here base, it is on left hand side because it is input terminal. Then emitter at bottom side because it is the common terminal. So here I am having emitter, then this is collector, and here I am having base. And one resistor is connected at the input, that is RB, and here I am applying the input voltage. Then emitter is grounded. Then in series with collector, I am having a resistor, that is RC, and here I am applying plus VCC. So this is the simple circuit in which this BJT can be used as a switch. So you can see here, input is given to the base, then here we will measure the output between the collector and emitter. So VC is the output. Here the potential at this here it is plus VCC. Obviously it is with respect to ground. So it indicates that here there is actually a DC supply between this VCC point and ground point, and whose negative terminal is nothing but the ground point, and positive is nothing but plus VCC. So at emitter terminal the potential is 0, and if this is the VCC supply, the positive terminal will be at plus VCC. So this is simple analogy for your understanding. Now I will remove this because you have understood. Plus VCC means it is with respect to ground point. It is with respect to ground point, that is emitter terminal. Now first case, if this input potential, input voltage, it is equal to 0. So 0 potential means the base current IB will be 0, and if IB is equal to 0, we know that in this common emitter configuration, the current gain beta is equal to output current IC divided by input current IB. Hence, output current IC is equal to beta times IB. If IB is 0, then IC will be also 0, and if IC is 0, no current is flowing through the transistor. And here in this case, if you consider this transistor, it is NPN transistor, NPN. The P and N, they are at same potential, so that is why base emitter junction is reverse bias. And the N side here at collector, it is a higher potential as compared to the base, so that is why both the junctions are reverse bias. Hence this transistor here in this case, when we put it 0, it will act in as an open switch, that is off switch, and it will operate in cutoff region. Now its equivalent circuit I can show you here. Its equivalent circuit. Here you will have this RC, then this is plus VCC. Then here there is emitter terminal, this is collector terminal, and here the transistor is acting as an off switch, you can see here. Hence the output voltage between collector and emitter, it is equal. Now if you see, what is the current flowing through the RC? It is 0. So that is why there is no drop across RC. Hence the potential at one side of RC will be same as that of second side. So at this point, at collector point, the potential in this case, it is same as that of VCC. And hence the VC, which is equal to potential at collector minus potential at emitter, it is equal to VCC minus the potential at emitter is 0. So that is why it is equal to VCC. So this is nothing but the value of VC in cutoff region. We know that, we have seen it in last video. So this is the, here the transistor is acting as an off switch. Here transistor is acting as an off switch. Now if you consider the second case, if this input is not 0, if the input is not 0 and input is positive with respect to the potential at emitter, that is input is greater than 0 volt, then what will happen? Now if you apply the Kirchhoff's voltage law to the input side, what is there? There is input potential, then there is some drop across this RB, then there is drop between the base and emitter. So that is why if I apply the Kirchhoff's voltage law to this input loop, that is base emitter loop, then get the equation that is nothing but plus V in, then minus VBE minus VB. Before that, sorry, minus VB. Before that, we will have some drop across this RB. That is nothing but minus IB into RB minus VB is equal to 0. Hence, if you find the value of IB is equal to V in minus VBE divided by RB. So let us consider this is equation number 1. So in this equation number 1, the VB, when it is forward bias, it is a PN junction and its value is fixed near about 0.7 volt. So it is fixed, RB is fixed. So the input is variable and hence the base current is dependent on the this input voltage. Now second, we know that in common emitter configuration, the current gain beta, it is equal to IC by IB. Hence the output current IC is equal to beta times IB. So let us consider this is equation number 2. And if I consider the output side, which is in between collector and emitter, if I apply Kirchhoff's voltage law, then I have VCC, then minus ICRC, then minus VC is equal to 0. So what I get? Here I get one more equation at the output side, plus VCC minus ICRC, then minus VC is equal to 0. Hence, the IC will be equal to VCC minus VC divided by RC. Say equation number 3. Now consider equation number 1. If you increase the input voltage, what will happen? Base current will increase, and if base current is increased, beta is constant for given transistor, the collector current will also increase. If the collector current is increased, right? So this collector current will increase, but there is some limitation on increase in the collector current. Why? If the collector current is increased, as VCC is constant, RC is constant, VCC is constant, RC is constant, there should be decrease in VC, that is the output voltage. And this VC can be decreased up to only its saturation level, that is 0.7 volt. So in saturation level, if I consider the VC is sat, right? The corresponding value of saturation current is IC sat, right? So if you increase the input voltage, base current will increase, there will be increase in collector current, and there will be decrease in VC. But there is certain limitation, minimum value of VC, beyond which it cannot be decreased, that is 0.7 volt. So the maximum value of the collector current that can be increased will be given by this equation number 3. Beyond that, it cannot be increased though you are increasing the base current, means though you are increasing the input. This is called saturation point. So when transistor reaches to the saturation point, what will happen? There will not be increase in collector current though there is increase in the base current, And if you consider this diagram now, the emitter which is at N type, base which is at P type. P type is at higher potential as compared to N type. So base emitter junction is forward bias, and the magnitude of this input voltage is adjusted such that this collector base junction is forward bias in saturation region. So here both the junctions are forward bias, and transistor, it will now act as a closed switch, that is on switch. And its equivalent circuit, I will show here simple, the equivalent circuit when it operates as an on switch. Here it is having RC, then this is plus VCC, then this is the collector terminal, this is the emitter terminal, there is closed switch between these two. So you can see this is the equivalent circuit when transistor, both the junctions are in saturation forward bias, and transistor is operating in saturation region. The transistor will act as a closed switch here. And if you measure the output voltage, that is nothing but Vc. It is the potential at collector with respect to emitter. It is equal to 0 now. It is equal to 0 now. And here the transistor is on switch. Transistor is on switch. So if you see this is the simple circuit. Then when both the junctions are reverse bias, transistor equivalent circuit, it acts as an off switch. Output voltage is equal to Vcc. And when both the junctions are forward bias, its equivalent circuit is shown here. Transistor will act as an on switch, and output voltage Vc is equal to 0. So this is the transistor as a switch. If you carefully see this circuit, right, the same circuit is acting as a logic inverter. What is logic inverter? If you give logic 0 input, the output is logic 1. And if you give logic 1 input, output is logic 0. So in digital electronics, we are in only two logic levels. Logic 0 means 0 volt, and logic 1 is say plus 5 volt. Here what I have done, in first case, if I give 0 input is 0, is logic 0, I am getting the output VCC, means logic 1. And if I give input say plus 5 volt, that is logic 1, I am getting the output 0, means logic 0. So that is why this same circuit is can be used as a logic inverter. Thank you.